May 1, 1943, RAF Coningsby, Lincolnshire, England. Flight Lieutenant John Hopgood stood in the debriefing room, his hands shaking as he tried to light a cigarette. His Lancaster bomber, identification code ED-906AJM, had returned from a training mission with damage that shouldn't have been survivable. The entire port outer wing section, outboard of the second engine, was gone. Not damaged. Torn away by a collision with telephone wires during a low-level navigation exercise. "I don't know how we stayed in the air," Hopgood told the intelligence officer. "The aircraft wanted to roll left continuously. Full right aileron barely kept us level. The rudder was fighting me the entire way back. My co-pilot and I, both of us on the controls, maximum strength, for 40 minutes straight." The engineering officer examining the damaged Lancaster was equally baffled. By every calculation, by every principle of aerodynamics he understood, the aircraft should have entered an uncontrollable roll and crashed immediately. The asymmetric lift should have been impossible to counteract. Yet here sat the bomber, missing perhaps 15 feet of its port wing, having flown 40 miles back to base and landed successfully. What the officers in that debriefing room could not know was that they were witnessing the beginning of a phenomenon that would be repeated dozens of times during the war. Bombers, primarily British Lancasters and American B-17s and B-24s, would lose substantial portions of their wings to enemy fire, collisions, or structural failures, yet remain controllable enough for their crews to bring them home. These incidents would challenge conventional understanding of aircraft stability and control, force the development of new flying techniques, and ultimately save hundreds of lives. This is not a story about aircraft design, though design played a critical role. It is not a story about luck, though luck was certainly involved. This is a story about pilots who, faced with impossible situations, discovered through desperation and skill that heavy bombers could be controlled and landed, even when basic aerodynamic principles suggested they should be uncontrollable. Today we will examine every aspect of this phenomenon. We will understand the aerodynamics that made these survivals possible against all probability. We will follow specific incidents where crews managed to land catastrophically damaged bombers. We will explore the training and techniques that evolved from these experiences. We will analyze the aircraft characteristics that made some bombers more survivable than others. And we will hear from the pilots themselves about what it felt like to fight an aircraft that wanted to kill them, using every ounce of strength and skill to reach home. This is the story of the pilots who learned to land bombers with one wing. To understand why landing a bomber with severe wing damage should be impossible, we must first understand how aircraft generate lift, maintain stability, and respond to control inputs. The principles are straightforward in theory but become extraordinarily complex when major portions of the lifting surface are destroyed. An aircraft wing generates lift through the pressure differential created as air flows over its surfaces. The wing's airfoil shape causes air traveling over the top surface to move faster than air traveling underneath. This speed differential creates lower pressure above the wing and higher pressure below, producing an upward force we call lift. For an aircraft in level flight, the total lift from both wings must equal the aircraft's weight. A Lancaster bomber at typical operating weight of 68,000 pounds requires 68,000 pounds of lift to maintain level flight. In normal operations, this lift is distributed symmetrically across both wings, with each wing producing approximately 34,000 pounds. The wings are identical in size and shape, operating at the same angle of attack, generating equal lift. When a significant portion of one wing is destroyed or torn away, the symmetry is catastrophically disrupted. Consider a Lancaster that loses the outer 15 feet of its port wing, approximately 30% of that wing span. The lifting area is reduced by roughly the same percentage, meaning the port wing can now generate only about 24,000 pounds of lift instead of 34,000 pounds. The starboard wing, undamaged, continues producing its full 34,000 pounds. This 10,000-pound differential creates an enormous rolling moment around the aircraft's longitudinal axis. The starboard wing, generating more lift, tries to rise. The port wing, generating less lift, tries to fall. The result is a powerful tendency to roll left, toward the damaged wing. This rolling moment must be counteracted if the aircraft is to remain controllable. The primary means of counteracting roll is through the ailerons, movable control surfaces on the trailing edges of the outer wing sections. When the pilot moves the control column to the right, the port aileron deflects downward, and the starboard aileron deflects upward. The downward deflected port aileron increases the lift on the port wing. The upward deflected starboard aileron decreases the lift on the starboard wing. These differential lift changes create a rolling moment to the right, opposing the leftward roll from the asymmetric lift. But here's the fundamental problem. If the outer section of the port wing is gone, so is the port aileron. The pilot has lost perhaps 40% of his roll control authority. He still has the starboard aileron, which can reduce lift on the starboard wing, but he cannot increase lift on the port wing where it's desperately needed. His control authority is halved at the moment he needs it most. The pilot has two remaining tools, rudder and differential thrust. The rudder, a vertical control surface on the tail, normally controls yaw, the aircraft's rotation around its vertical axis. But yaw and roll are coupled in aerodynamics through a phenomenon called dihedral effect. When an aircraft yaws to one side, the wing on that side moves forward through the air slightly faster, generating more lift, which creates a rolling moment. By applying right rudder, deflecting the rudder to the right, the pilot causes the aircraft to yaw right. This increases the lift on the port wing through the dihedral effect, helping to counteract the roll. But this is an indirect and inefficient means of generating roll control. The rudder is designed for yaw, not roll. Using it for roll control requires large rudder deflections that create significant drag and make the aircraft want to slip sideways through the air. Differential thrust provides another option. A Lancaster has 4 Merlin engines, 2 on each wing. If the pilot reduces power on the starboard engines and increases power on the port engines, the asymmetric thrust creates a yawing moment that can help counteract the roll. But this technique reduces total thrust at a moment when the damaged aircraft desperately needs all available power. The increased drag from the damaged wing and the deflected control surfaces means the bomber is flying less efficiently, requiring more power just to maintain level flight. The mathematical reality is stark. For a Lancaster that has lost 30% of one wing, the rolling moment might be on the order of 250,000 foot-pounds. The remaining aileron, at full deflection, might generate a counteracting moment of 150,000 foot-pounds. The rudder at maximum deflection might contribute another 50,000 foot-pounds through dihedral effect. Differential thrust might add 20,000 foot-pounds. The pilot is 30,000 foot-pounds short of the force needed to maintain level flight. This deficit means the aircraft will roll continuously toward the damaged wing unless the pilot accepts a permanent bank angle to the right. By banking the aircraft to the right, the pilot allows the horizontal component of lift from the wings to balance the rolling moment. The aircraft flies in a continuous turn, but it can be controlled. The required bank angle can be calculated from the force imbalance. For our hypothetical Lancaster, the mathematics suggests a bank angle of approximately 15 to 20 degrees to the right would be needed to maintain controlled flight. This bank angle means the aircraft is constantly turning, making straight flight impossible. To maintain a heading, the pilot must make a series of turns, banking more steeply to turn away from the damaged wing, then reducing bank to turn back. But this analysis assumes the pilot can actually hold these control positions. The control forces required to maintain full aileron, maximum rudder, and differential thrust for extended periods are enormous. A Lancaster's controls are not hydraulically assisted. Every control input requires the pilot to physically move cables and pulleys that deflect control surfaces fighting against aerodynamic forces. At normal cruising speeds, holding full aileron deflection for more than a few minutes becomes physically exhausting for even the strongest pilot. The control column forces can exceed 50 pounds, meaning the pilot is essentially doing a one-armed bench press continuously while also flying the aircraft. After 10 minutes, fatigue becomes overwhelming. After 30 minutes, maintaining control requires 2 crew members, pilot and co-pilot, both pushing on the controls with maximum effort. The rudder forces are similarly extreme. Full rudder deflection at cruising speed can require over 100 pounds of pedal force. The pilot must maintain this force continuously, his leg muscles straining, while simultaneously managing aileron forces and monitoring dozens of other parameters. The physical demands approach the limits of human endurance, and this assumes the damage is limited to the wing. In reality, bombers returning with missing wing sections often have additional damage. Engines may be shot out, reducing available power. Hydraulic systems may be compromised, increasing control forces. Electrical systems may be damaged, eliminating instruments. Fuel may be leaking, limiting endurance. Crew members may be wounded, unable to assist with control inputs. The combination of these factors creates a situation where survival should be statistically impossible. Yet the historical record documents dozens of cases where bomber crews successfully brought home aircraft with catastrophic wing damage. The question is not whether it happened, the documented cases are irrefutable, but how it was possible and what enabled certain crews to succeed where others would have failed. The phenomenon of bombers surviving major wing damage was not recognized as such during the early years of the war. Individual incidents occurred and were reported, but they were treated as isolated cases of extraordinary luck rather than as a pattern suggesting something about aircraft design or crew capability. The first incident that received significant attention involved AB-17, flying fortress over Germany in 1943. On April 17, 1943, Second Lieutenant Roberts Johnson was piloting a B-17F, serial number 4229649, aircraft identification Hell's Angels, with the 303rd Bomb Group. The mission was an attack on the Focke-Wulf aircraft factory at Bremen, one of the most heavily defended targets in Germany. The 303rd formation encountered intense fighter attacks during the bomb run. A Focke-Wulf 190 made a head-on attack, closing at a combined speed of nearly 500 miles per hour. The German pilot's 20mm cannon fire walked across Hell's Angels' starboard wing, exploding along the wing's leading edge. The outer engine, number 4, was hit and immediately caught fire. But more critically, the cannon shells severed the main spar approximately 6 feet inboard of the engine. The structural failure was catastrophic. The outer wing section, including the engine and aileron, folded upward at an angle of nearly 45 degrees. Only the wing's lower skin and some secondary structure prevented the section from tearing away completely. The folded wing section created enormous drag and completely eliminated lift from that portion of the wing. Johnson felt the aircraft snap violently to the right as the asymmetric forces took hold. His instinctive reaction was to haul back on the control column and push full left aileron, trying to level the wings. The B-17 responded sluggishly, the nose coming up but the bank continuing to increase. The aircraft was entering a spiral dive. The co-pilot, Second Lieutenant John Wynant, grabbed the control column and added his strength to Johnson's. Together, they managed to arrest the roll at approximately 30 degrees of bank and stabilized the aircraft in a descending turn. But any attempt to level the wings resulted in an immediate roll back to the right. The B-17 would only fly in a continuous right turn. "We're going down," Johnson reported over the intercom. "Prepare to bail out." The crew began destroying classified materials and preparing parachutes. The bombardier opened the nose hatch. The navigator put on his parachute and moved toward the exit. But Johnson and Wynant continued fighting the controls, trying different control inputs, experimenting with power settings. They discovered that by reducing power on the two starboard engines and increasing power on the port engines, they could reduce the turning tendency. By adding maximum left rudder, they could further flatten the turn. And by accepting a permanent 20-degree bank to the left, they could maintain something approximating controlled flight. The bomber descended from 22,000 feet to 5,000 feet during this experimentation, constantly turning right but maintaining enough control that Johnson decided to attempt reaching England rather than ordering a bailout over Germany. The navigator calculated a heading, and Johnson began the delicate process of steering the aircraft by varying the turn radius. To turn left, he steepened the bank. To turn right, he shallowed it. It was more like sailing a ship than flying an aircraft, but it worked. The journey back to England took over 2 hours, with Johnson and Wynant spelling each other on the controls every 15 minutes as fatigue overwhelmed them. They flew at 5,000 feet, low enough that German fighters could easily attack but high enough to glide to the channel if the remaining engines failed. No further attacks came, whether from luck or because the German fighters had exhausted their ammunition and fuel was never determined. Crossing the English coast near Ipswich, Johnson faced his final challenge: landing the crippled bomber. The normal landing pattern was impossible because the aircraft could only turn right and the runway orientation required left turns. Johnson flew past the base, made a wide right turn to come back around, then another right turn to line up on final approach. The landing itself was surprisingly uneventful. The damaged starboard wing wanted to drop during the landing flare, but Johnson had learned to anticipate this and compensated with aileron and rudder. The B-17 touched down firmly but safely, rolling to a stop with brake application on the port side only, as the starboard brake lines had been damaged by the same cannon fire that struck the wing. The ground crew who examined Hell's Angels were astonished that it had flown at all, much less made it back from Germany. The structural engineer calculated that the folded wing section should have created enough drag and lift asymmetry to make the aircraft uncontrollable. The pilot's report was initially treated with some skepticism. Surely he must be exaggerating the damage, or conditions couldn't have been quite as bad as described. Then photographs were developed showing the full extent of the damage, and the skepticism turned to bewilderment. Hell's Angels had flown for over 2 hours with damage that aeronautical engineers insisted should have caused immediate loss of control. The incident report was forwarded to the Army Air Force's Technical Command for analysis, where engineers began theoretical studies of asymmetric flight. The second well-documented case occurred just 6 weeks later, involving a Lancaster bomber from RAF 617 Squadron, the famous Darmbusters unit. On May 16, 1943, during the actual Dams raid that would make the squadron legendary, Flight Lieutenant John Hopgood's Lancaster was hit by flak while attacking the Mimchen Dam. The anti-aircraft fire struck the port wing between the fuselage and inner engine, causing a fuel tank to explode. The explosion and subsequent fire weakened the wing's structure. As Hopgood pulled up after releasing his bouncing bomb, the damaged wing section collapsed and tore away. Approximately 12 feet of wing, including the port inner engine and part of the main fuel tank, simply separated from the aircraft. The Lancaster immediately rolled left. Hopgood and his flight engineer, Sergeant John Brennan, both grabbed the controls and hauled right with all their strength. The bomber stopped rolling at about 40 degrees of bank but refused to level further. The two men held the controls in this position while Hopgood assessed the situation. Unlike Johnson's B-17, which had time to experiment over relatively safe territory, Hopgood was at low altitude over heavily defended enemy territory with a badly damaged aircraft. He had seconds to decide: order bailout or attempt to fly the aircraft home. The intercom was dead, destroyed by the same flak that had hit the wing, so Hopgood couldn't communicate with most of his crew. Hopgood made the decision to fly. He pointed the bomber west, toward Holland and the North Sea, maintaining 500 feet of altitude and a constant 30-degree bank to the right. The asymmetric drag from the damaged wing meant the Lancaster could barely maintain 150 miles per hour, well below normal cruising speed. The fuel situation was critical. One of the main tanks was gone, and gauges showed the remaining fuel draining rapidly from damaged lines. The Lancaster reached the Dutch coast and crossed into neutral airspace. Over the North Sea, Hopgood held the controls while Brennan went back through the fuselage to assess damage and casualties. 3 crew members were dead, killed by the flak or the subsequent fire. The survivors, 4 men including Hopgood and Brennan, were uninjured but exhausted. 20 miles from the English coast, the fuel exhaustion warnings illuminated. The remaining engines began sputtering. Hopgood made the decision to ditch rather than risk the aircraft breaking up during landing. He reduced power, lowered the nose, and put the Lancaster into the North Sea at approximately 120 miles per hour. The ditching was violent. The damaged wing hit first, causing the bomber to cartwheel. The aircraft broke apart, the fuselage section separating from the wings. Hopgood and 2 other crew members escaped the sinking wreckage and were rescued by Royal Navy vessels within 30 minutes. The 4th survivor was trapped in the wreckage and drowned. The significance of Hopgood's feat was recognized immediately within 617 Squadron. He had kept a catastrophically damaged bomber under control for nearly 45 minutes, covering over 100 miles, and had even executed a controlled ditching. The intelligence from this incident, combined with the Hell's Angels case from a month earlier, prompted both British and American Air Forces to begin systematic studies of asymmetric flight characteristics. These studies would eventually lead to changes in training, development of new techniques, and formal procedures for handling severe battle damage. But in mid-1943, these were still isolated incidents. The vast majority of crews facing similar damage did not survive, either because they were unable to maintain control long enough to escape enemy territory, or because they faced circumstances, night conditions, additional damage, crew casualties that made survival impossible regardless of skill. What separated the survivors from the casualties would become a subject of intensive study. Was it aircraft type, with some bombers being more tolerant of asymmetric damage than others? Was it crew experience and training? Was it luck, being hit in ways that damaged the wing but left control systems and engines intact? Or was it some combination of all these factors? As reports of successful survivals accumulated through 1943 and 1944, aeronautical engineers at Wright Field in Ohio and the Royal Aircraft Establishment at Farnborough, England, began systematic studies of how heavily damaged bombers could remain controllable. The research involved theoretical analysis, wind tunnel testing, and eventually, deliberate flight tests with progressively damaged aircraft. The theoretical analysis started with basic force and moment calculations. Engineers modeled a bomber as a rigid body with known mass properties and aerodynamic characteristics. They calculated the forces and moments generated by various damage scenarios, from losing small wing sections to losing entire outer wing panels. The calculation suggested that bombers should be uncontrollable with more than about 15% of one wing destroyed. But the field reports contradicted this conclusion. Bombers were surviving with 25, 30, even 40% of a wing missing. Something in the theoretical models was wrong or incomplete. The engineers needed to understand what factors they were missing. Wind tunnel testing provided the first clues. Scale models of B-17s and Lancasters were mounted in wind tunnels with removable wing sections. Technicians could remove portions of one wing and measure the resulting forces and moments on the model. The tests revealed several effects that the simplified calculations had missed. First, the dihedral angle of the wings, the upward angle from root to tip, created a stabilizing effect that partially compensated for asymmetric lift. Both the B-17 and Lancaster had significant dihedral, designed to improve lateral stability in normal flight. This dihedral became even more important during asymmetric flight, generating restoring moments that opposed the rolling tendency. Second, the fuselage itself generated aerodynamic forces during asymmetric flight. When the aircraft rolled and yawed, the fuselage presented an angled surface to the airstream, generating lift and side forces that contributed to the overall force balance. In some configurations, the fuselage lift actually helped counteract the wing asymmetry. Third, and most importantly, the vertical tail and rudder were more effective than the simple calculations suggested. The large tail area of heavy bombers, designed to provide directional stability with asymmetric engine power, proved capable of generating substantial side forces. When used at maximum deflection, the rudder could create yawing moments that, through dihedral effect and coupling between roll and yaw, partially counteracted the rolling moment from the damaged wing. The wind tunnel data suggested that bombers with large vertical tails, high dihedral, and substantial fuselage volume might remain marginally controllable even with severe wing damage. This correlated well with field reports, B-17s and Lancasters. Both featuring these characteristics had higher survival rates than aircraft with smaller tails or less dihedral. But wind tunnel testing had limitations. The models could not replicate control system forces or pilot inputs. A model in a wind tunnel would simply reach an equilibrium position based on the forces acting on it. A real aircraft required continuous pilot inputs, fighting against control forces that changed with airspeed, altitude, and control deflection. To understand the piloting task, engineers at Wright Field proposed flight testing with deliberately damaged aircraft. This was an extraordinarily dangerous proposition. They would take perfectly functional bombers, cut portions from their wings, and then ask test pilots to fly them. If the theoretical analysis was wrong, or if the damage exceeded controllability limits, the pilots would die. The program began cautiously in early 1944. A war-weary B-17F, tired from combat operations and scheduled for scrapping, was selected for the first test. Engineers cut away a 5-foot section from the outer port wing, removing approximately 10% of the wing's area. The damaged aircraft was theoretically controllable based on calculations, but no one knew if a human pilot could actually fly it. Lieutenant Colonel Harold Watson, chief of the Flight Test Division at Wright Field, volunteered to make the first flight. Watson was an experienced test pilot with thousands of hours in various aircraft types, but he had never flown anything quite like this. The pre-flight briefing emphasized that if the aircraft proved uncontrollable, he should bail out immediately rather than trying to save it. The takeoff on March 15, 1944, was nerve-wracking for everyone watching. The B-17 accelerated down the runway with Watson applying full right aileron and right rudder from the start. At rotation speed, Watson pulled back on the control column and the bomber lifted off, immediately trying to roll left. Watson countered with more aileron and rudder, and the bomber stabilized in a 10-degree left bank. Climbing to 10,000 feet, Watson explored the handling characteristics. The aircraft would fly in a shallow left bank with full right control inputs. Reducing the control inputs allowed the bank to steepen. The bomber could be turned right by adding more right bank, and left by reducing it. Landing would be challenging but feasible. Watson flew for 45 minutes before landing successfully. His report noted that the control forces were manageable for short periods but would become exhausting on long flights. The test validated the theoretical predictions and confirmed that a 10% wing loss was survivable with skilled piloting. Subsequent tests increased the damage progressively. A second B-17 lost 15% of its wing, then 20%. Each configuration was flown by test pilots who documented handling characteristics, control forces, and flying qualities. The tests revealed that controllability degraded gradually as damage increased, not catastrophically. A skilled pilot could maintain control with up to about 25% wing loss, though the physical demands became extreme. The British conducted parallel tests at Farnborough using Lancaster bombers. Their results largely mirrored the American findings, though the Lancaster's different control system characteristics meant that specific handling details varied. The Lancaster's controls were less harmonized than the B-17's, with relatively heavy aileron forces and lighter rudder forces. This made asymmetric flight techniques slightly different between the two aircraft types. One critical discovery from both test programs was the importance of airspeed. At higher airspeeds, the control surfaces generated more force for a given deflection, improving controllability. But higher airspeed also increased the loads on the damaged wing structure, risking further structural failure. The optimal airspeed was a compromise, fast enough for good control authority, slow enough to avoid overstressing the weakened structure. For both B-17s and Lancasters, this optimal speed was approximately 160 to 180 miles per hour, significantly slower than normal cruising speeds of 200 to 220 miles per hour. Flying at reduced speed meant longer exposure to enemy fighters and flak, increased fuel consumption relative to distance covered, and reduced time to react to emergencies. But it was necessary to maintain controllability without risking structural collapse. The test program also revealed significant pilot technique factors. Different pilots flying the same damaged aircraft achieved different results based on their control inputs and energy management. The most successful pilots developed a feel for the aircraft's behavior, anticipating changes and making small, smooth corrections rather than large, abrupt inputs. This finding led to the development of formal training procedures for asymmetric flight. Selected experienced pilots were trained using the test aircraft, learning techniques that could be passed on to operational crews. The training emphasized several key principles: immediate recognition of damage and assessment of controllability, establishing a stable flight condition before attempting navigation, using all available controls, aileron, rudder, and differential thrust in coordination, accepting non-standard attitudes and flight paths if necessary to maintain control, conserving pilot energy through technique and crew coordination, planning approaches and landings that accommodated the aircraft's limitations. Perhaps the most important discovery was the value of crew coordination. A single pilot could maintain control of a severely damaged bomber for perhaps 15 or 20 minutes before fatigue overwhelmed him. But with two pilots alternating on the controls, or with the flight engineer or bombardier assisting, control could be maintained indefinitely. The key was recognizing early that assistance would be needed and organizing the crew accordingly. The research also investigated which parts of the wing were most critical. Damage to the outer wing sections, beyond the ailerons, was more survivable than damage to inner sections near the fuselage. This was counterintuitive. Losing outer sections removed more area, but made sense aerodynamically. The outer wing generated relatively less lift per foot of span, so losing it created less force imbalance. More importantly, losing outer sections usually left the ailerons intact, preserving roll control authority. Conversely, damage between the fuselage and engines was most dangerous. This region of the wing generated substantial lift due to its high chord width and location in relatively undisturbed airflow. Losing this section created large force imbalances. Additionally, damage in this region often affected fuel tanks, engines, and control runs, compounding the controllability problem with other failures. These findings influenced both tactical doctrine and aircraft design. Tactical planning began routing bombers to avoid the most heavily defended areas where possible, reducing the likelihood of the worst types of damage. Design improvements in subsequent bomber models incorporated lessons learned, including strengthening critical wing structures, providing redundant control paths, and improving crew coordination features. But for the thousands of bomber crews flying missions in 1943, 1944, and 1945, these research findings came too late or remained unknown. They faced the reality of asymmetric flight without benefit of formal training or tested procedures. Their survival depended on instinct, improvisation, and sheer determination qualities that no amount of engineering research could quantify or predict. While engineering research provided theoretical understanding of asymmetric flight, the true test came in combat conditions where pilots faced not only aerodynamic challenges but also enemy action, weather, crew casualties, and equipment failures. Several incidents from 1943 to 1945 became legendary within bomber commands, studied for the lessons they provided and the extraordinary airmanship they demonstrated. The incident involving B-24 Liberator Strawberry Bitch on March 18, 1944, exemplified the extreme conditions under which some crews managed to survive. First Lieutenant Henry Red Irwin was piloting the B-24 during a raid on Friedrichshafen, Germany, targeting the Dornier aircraft factories. The mission encountered heavy fighter opposition, with Luftwaffe FW-190s and Bf-109s attacking in waves. During one attack, a 20mm cannon shell struck the B-24's starboard wing at the root, where it joined the fuselage. The shell penetrated the main spar and detonated, severing approximately 40% of the spar's cross-section. The wing remained attached, but the structural damage was severe. The wing began flexing dramatically during flight, bending up and down by several feet at the tip with each gust or control input. More critically, the cannon fire had also struck the No. 3 engine, the inboard engine on the damaged wing. The engine seized immediately, its propeller windmilling in the airstream and creating enormous drag. Irwin hit the feathering button to stop the propeller's rotation, but the feathering mechanism had been damaged and didn't respond. The propeller continued windmilling, each blade creating drag equivalent to a large barn door being held perpendicular to the airstream. The combination of reduced wing strength, asymmetric lift from the damaged wing, and massive drag from the windmilling propeller created an almost impossible flight condition. The B-24 rolled violently to the right and entered a descending spiral. Irwin and his co-pilots, Second Lieutenant James Brown, both grabbed the controls and pulled with maximum force. The bomber's roll slowed but didn't stop. The nose continued dropping despite full back pressure on the control column. "We're done," Brown said over the intercom. "Give bailout order." But Irwin had noticed something during the attempted recovery. When he reduced power on the 3 operating engines, the nose came up slightly. When he added power, it dropped. This was counterintuitive normally, adding power would help hurry. But with the enormous drag from the windmilling propeller, adding power on the operating engines was making the asymmetry worse, not better. Irwin reduced all 3 operating engines to idle. The B-24's descent rate increased without power. They were now gliding, but the nose came up and the spiral shallowed. With careful control inputs, Irwin stabilized the bomber in a 30-degree right bank, descending at 500 feet per minute. "Cancel bailout," Irwin transmitted. "We're going to fly this back." The navigator calculated that from their current altitude of 18,000 feet and position, approximately 300 miles from the Swiss border, they could just barely glide to Switzerland if they lost no more altitude than necessary. Switzerland was neutral internment was preferable to becoming POs in Germany. The glide to Switzerland took 36 minutes. Irwin and Brown maintained control through constant, coordinated inputs, never allowing the bomber to deviate from the precarious balanced condition they'd established. The flight engineer monitored the damaged wing, reporting each time the flexing seemed to worsen. The crew threw out everything they could to reduce weight guns, ammunition, equipment, anything not essential. They crossed into Swiss airspace at 8,000 feet, finally allowing themselves to believe survival was possible. Irwin selected a suitable field and began the approach. The landing was hard with no engine power. Irwin couldn't adjust the descent rate in the flare, but the B-24 touched down, rolled across a Swiss farmer's field, and came to rest with the damaged wing collapsing completely as forward motion stopped. Swiss military forces interned the crew for the duration of the war. Irwin received the Distinguished Service Cross for his airmanship. Post-war analysis of the structural damage concluded that the wing should have failed completely during the high-G maneuvering required to recover from the initial spiral. That it held together long enough for the gliding landing qualified as what one engineer called structural miracle combined with aerodynamic improbability. Another legendary incident occurred on October 14, 1943, Black Thursday, during the disastrous second raid on Schweinfurt. The 381st Bomb Group lost 4 B-17s over the target, and several more were badly damaged. One of the damaged aircraft was B-17F Lucky 13, piloted by Lieutenant Robert Hughes. German fighters made repeated attacks on Lucky 13 during the withdrawal from the target. One Bf-109 made a deliberate ramming attack, its wing striking Lucky 13's port wing approximately 5 feet outboard of the No. 2 engine. The collision was catastrophic. The German fighter disintegrated, killing its pilot instantly. Lucky 13's port wing crumpled, the outer 7 feet of the wing folding back against the rest of the wing structure. The B-17 snap-rolled left and entered a flat spin. Hughes and his co-pilot fought the controls desperately, but the aircraft continued spinning, descending through 20,000 feet, then 15,000, then 10,000. At 8,000 feet, Hughes ordered the crew to bail out. Men began moving toward the exits. Then something changed. The folded wing section, which had been pressed back against the intact wing by aerodynamic forces, suddenly flexed forward slightly. The change in configuration altered the airflow just enough that the B-17's spin slowed momentarily. Hughes and his co-pilot seized the opportunity, applying full right aileron, full right rudder, and maximum right engine power. The B-17 lurched, the spin stopped, and the bomber transitioned into a spiral dive that they could control. "Hold on," Hughes transmitted. "We're going to save her." The recovery from the dive required careful energy management. Too rapid a pullout would overstress the damaged wing. Too gentle, and they'd lose too much altitude. Hughes modulated the back pressure on the control column continuously, feeling for the edge of structural limits. At 2,000 feet above the German countryside, the B-17 leveled off, flying in a 40-degree bank that Hughes and his co-pilot maintained with continuous maximum control inputs. The bomber was now too low and too slow to reach England. German fighters could easily finish them off. But they were heading west toward France, and there was a slim chance of making Allied-held territory. More importantly, Hughes had 4 crew members still aboard who deserved every chance to survive. Lucky 13 flew for another 45 minutes, crossing into France at 1,500 feet altitude. The damaged wing was visibly flexing, moving up and down by at least 3 feet at the tip. Hughes could feel each flex through the control column as the wing's changing shape altered the lift, distribution, and required constant control corrections. The physical demands were overwhelming both pilots, requiring them to switch positions every 5 minutes. Over Normandy, still occupied by German forces in October 1943, the decision point came. The bomber had perhaps 20 minutes of fuel remaining. They were not going to make England. Hughes could either try to land in occupied France, likely being captured, or turn back toward the English Channel and ditch in the water where air-sea rescue might find them. Hughes chose the water. He turned north, coaxing every mile from the remaining fuel. The bomber crossed the coastline at 800 feet. 10 miles offshore, both remaining engines on the port side quit as the last fuel was consumed. With only one engine running on the starboard side, the asymmetric thrust made control even more difficult. "Ditch positions," Hughes commanded. The 4 remaining crew members secured themselves in the radio room, the most protected area for ditching. Hughes and his co-pilot stayed in the cockpit, fighting the controls as the B-17 descended toward the cold waters of the English Channel. The ditching at 120 miles per hour was violent but survivable. The damaged wing hit first and collapsed completely, causing the bomber to cartwheel once before settling into the water. The fuselage broke into 3 sections. Hughes and his co-pilot escaped through the shattered windscreen. The 4 men in the radio room climbed out through the top hatch before that section sank. All 6 survivors were rescued by a Royal Navy launch within 90 minutes. They spent 3 weeks hospitalized for injuries ranging from broken bones to hypothermia, but all recovered. The story of Lucky 13's survival spread rapidly through the 8th Air Force, becoming a symbol of what was possible with skill, determination, and luck. The question of luck versus skill in these incidents occupied many discussions among pilots and engineers. Clearly, luck played a role, being hit in ways that damaged but didn't destroy, having the damage occur over territory where survival was possible, having weather conditions that permitted flying the damaged aircraft. But the survivors consistently demonstrated exceptional airmanship, making decisions under extreme stress that proved to be correct. One incident that illustrated the importance of decision-making involved Lancaster bomber ND-654 from RAF 115 Squadron on December 29, 1944. Flying Officer Derek Jackson was pilot on a mission to the Schalvenboer oil refinery. Heavy flak over the target struck the Lancaster's port wing, causing an explosion in the fuel tanks. The explosion didn't just damage the wing, it blew away approximately 18 feet of the outer wing panel, from the outer engine nacelle to the tip. Jackson's immediate instinct was to roll the aircraft right to counteract the expected left roll. But during training, he had attended a lecture by a pilot who had survived similar damage. The lecturer had emphasized that the first moments after damage were critical for assessing controllability, and that sometimes the aircraft's natural response was actually the correct one. So instead of immediately fighting the controls, Jackson let the Lancaster respond naturally for just 2 seconds, watching what it did. The bomber rolled left, as expected, but the roll rate was not accelerating, it was actually slowing. The aircraft stabilized at about 30 degrees left bank with minimal control input. Jackson recognized what was happening. The dihedral effect and rudder authority were actually providing enough restoring force that only minimal aileron input was needed. If he had immediately applied full right aileron as instinct demanded, he would have been fighting against the aircraft's natural stability, making control harder rather than easier. This observation allowed Jackson to establish a control technique that minimized fatigue. He used small aileron inputs to fine-tune the bank angle, letting the aircraft's inherent stability do most of the work. He used rudder primarily to control heading, accepting that the heading changes would be slow and require planning ahead. And he managed power carefully to maintain speed without overstressing the damaged wing. ND-654 returned to England and landed successfully at its home base. Jackson's after-action report emphasized the importance of not over-controlling damaged aircraft, and this lesson was incorporated into subsequent training. The incident demonstrated that skilled piloting involved knowing when not to fight the aircraft as much as knowing when to apply maximum effort. Not all famous incidents had happy endings. The crew of B-17G Memphis Belle, not the famous original Memphis Belle, but a later bomber with the same name, encountered severe damage on February 25, 1944, during a mission to Regensburg. Flak shredded the bomber's starboard wing, removing the entire outer panel and both engines on that wing. Pilot Major Robert Morgan, no relation to the original Memphis Belle's pilot, and his co-pilot attempted the standard recovery techniques. Maximum control inputs, differential thrust on the remaining engines accepting a steep bank. But the damage was too severe. Even with both pilots pulling with full strength, the B-17 continued rolling to the right, the roll rate slowing but never stopping. Morgan held the controls for nearly 3 minutes, the bomber spiraling downward through the overcast, before accepting that recovery was impossible. "Bail out! Bail out!" he ordered. 8 crew members successfully parachuted. Morgan and his co-pilot stayed with the aircraft attempting to control it until it was too late to bail out. Both died in the crash. Post-war analysis suggested that Morgan's aircraft had exceeded the controllability limits. The damage was simply too extensive for any pilot to overcome. But Morgan's decision to stay with the controls while his crew escaped probably saved 8 lives. Had he ordered immediate bailout when the damage occurred, the aircraft would have entered an uncontrolled spin immediately, making escape far more difficult for the crew in the rear of the aircraft. These incidents, and dozens like them, created a body of knowledge about asymmetric flight that gradually percolated through the bomber commands. Pilots shared stories in ready rooms, techniques were discussed during briefings, and successful recoveries were analyzed to extract lessons applicable to future crews. This informal knowledge transfer probably saved as many lives as formal training programs. By 1945, most experienced bomber pilots had at least heard of someone who had brought back a heavily damaged aircraft. The knowledge that survival was possible, that techniques existed for controlling asymmetric damage, gave crews hope and motivation to keep fighting for control rather than immediately bailing out. This psychological factor was perhaps as important as the technical skills involved. The accumulation of combat experience with severely damaged bombers led to significant changes in pilot training programs during 1944 and 1945. What had begun as individual incidents analyzed in isolation evolved into systematic training, based on proven techniques and realistic simulation of damage scenarios. The transformation began at the 8th Air Force's training bases in England, where replacement crews received final preparation before joining operational squadrons. Flight instructors who were themselves combat veterans began incorporating asymmetric flight exercises into the curriculum. These exercises initially consisted of simulated engine failures, requiring pilots to manage the asymmetric thrust and resulting yaw. But engine-out procedures, while valuable, didn't fully prepare pilots for the more severe asymmetry of major wing damage. The forces and control responses were different in magnitude and character. A bomber with one engine out could be controlled with moderate effort and flown normally except for some performance penalties. A bomber with severe wing damage required maximum continuous effort and could barely be controlled at all. To provide more realistic training, several combat-damaged aircraft that had been successfully recovered were retained at training bases rather than being scrapped. These aircraft, repaired just enough to be airworthy but retaining visible damage, served as demonstrators. Experienced pilots would fly them, allowing instructor pilots to observe the techniques required and then teach those techniques to students. Flight Lieutenant Thomas Sawyer, an instructor at RAF Warboys, flew one such aircraft regularly through late 1944. The Lancaster had lost approximately 8 feet of its port wing in combat and had been repaired with a shortened wing deliberately built to the damaged configuration. This created a permanent asymmetric condition that pilots could safely experience. The first time you fly it, the asymmetry is shocking, Sawyer later wrote in his training manual. Your every instinct screams to fight it, to force the aircraft level. But that wastes energy and achieves nothing. You must accept that the aircraft will never fly normally again. Your task is to work with the aircraft, not against it. Sawyer developed a training progression that proved highly effective. Students would first fly the damaged Lancaster with an instructor, observing how the instructor managed the controls. Then they would fly it themselves under close supervision, learning to feel the control forces and responses. Finally, they would fly simulated cross-country missions, practicing navigation and landing approaches while managing the asymmetric configuration. The training revealed significant individual differences among pilots. Some adapted quickly to asymmetric flight, developing intuitive feel for the unusual control responses. Others struggled, never becoming comfortable with the unfamiliar sensations. These differences seemed to correlate more with temperament than with raw flying skill. The best asymmetric flight pilots were those who remained calm under stress, who could accept non-standard situations, and who had the physical endurance to maintain control inputs for extended periods. Physical conditioning became recognized as a critical factor. The U.S. Army Air Forces implemented strength training programs specifically designed to build the upper body and leg strength needed for extended maximum control inputs. Pilots learned exercises they could do during long missions to prevent fatigue. Co-pilots received training in quickly relieving pilots on the controls without causing dangerous transients. The training also emphasized crew coordination in ways that went beyond normal procedures. The flight engineer, bombardier, and navigator in a bomber were not pilots, but they could assist with control inputs if properly trained. Several training bases developed programs, teaching non-pilot crew members how to help with aileron or rudder inputs under pilot direction. Squadron leader James Wilson, commanding officer of a Lancaster training unit, implemented an innovative program where every crew member spent time in the cockpit learning basic control inputs. You don't need to be a pilot to push on a control column or press a rudder pedal, Wilson explained. In an emergency, having even unskilled assistance can make the difference between maintaining control and losing it. The psychological aspects of surviving severe damage received increasing attention. Combat veterans who had successfully brought back damaged aircraft were brought to training bases to speak with replacement crews. Their accounts emphasized several consistent themes: the importance of not panicking, the value of systematic problem solving, even in extreme stress, and the need to maintain focus on the controllable aspects of the situation rather than dwelling on the damage. One particularly effective training technique involved staged emergencies during routine training flights. Without warning, an instructor would simulate major damage by restricting control movement or creating asymmetric conditions through throttle manipulation. The student pilot had to immediately recognize the situation, establish control, and navigate to a successful landing. These exercises were intensely stressful but proved valuable in preparing pilots for actual combat damage. The training curriculum also incorporated lessons about when to abandon aircraft versus when to attempt recovery. This was perhaps the most difficult judgment call facing any pilot with severe damage. Bailing out over enemy territory meant probable capture and imprisonment. Attempting to fly home risked dying in an uncontrollable aircraft. The decision had to be made quickly, often with incomplete information about the extent of damage. The guidelines that emerged from experience emphasized several decision factors. If the aircraft initially responded to control inputs at all, even if barely, attempting continued flight was usually worthwhile. If control could be established within the first minute after damage, the aircraft could probably be flown home. If the damage occurred over enemy territory but the aircraft could maintain altitude, attempting to reach friendly territory was rational. But if controls showed no response, if altitude loss was uncontrollable, or if the aircraft was breaking up structurally, immediate bailout was the only sensible choice. Landing techniques for asymmetric aircraft received extensive development. Normal landing patterns were designed for aircraft with symmetric handling. A damaged bomber that could only turn one direction or that required constant maximum control inputs needed different procedures. Training bases developed specialized patterns that accommodated these limitations. Landing techniques for asymmetric aircraft received extensive development. Normal landing patterns were designed for aircraft with symmetric handling. A damaged bomber that could only turn one direction or that required constant maximum control inputs needed different procedures. Training bases developed specialized patterns that accommodated these limitations. The standard technique for landing an aircraft that could only turn right, for example, involved approaching the airfield from the east, making a continuous right turn to line up with the runway, and then committing to the landing without possibility of going around. This required precise judgment of wind conditions, approach speed, and descent rate because there was no opportunity to correct mistakes. Several training bases constructed practice runways at unusual angles to their main runways, allowing pilots to practice approaches that required only right or only left turns. These practice runways weren't long enough for normal operations, but provided realistic training environments. For damaged aircraft procedures, the development of training programs was complicated by the reality that not all damage scenarios could be safely simulated. Flying an aircraft with actual structural damage was inherently dangerous, and the training value had to be weighed against the risk of killing student pilots. Some scenarios were simply too dangerous to practice and had to be learned through ground school and study of previous incidents. Film footage from gun cameras and wing-mounted cameras became valuable training aids. Several combat missions had been documented where aircraft sustained severe damage, and this footage provided vivid illustration of what pilots might face. Watching the wing fold or tear away, seeing the aircraft's violent response, hearing the intercom conversations of the crew gave students visceral understanding that no lecture could provide. By mid-1945, the training programs had matured significantly from their early ad hoc beginnings. Replacement crews arriving at operational squadrons had received at least basic instruction in asymmetric flight. Many had flown aircraft with simulated damage. All had studied documented cases and learned the techniques that had proven successful. While this training couldn't guarantee survival in severe damage situations, it significantly improved the odds compared to the early war years when pilots had no preparation for such circumstances. The question of whether formal training or combat experience mattered more remained debated. Some veteran pilots argued that no amount of training could truly prepare someone for the reality of combat damage, that only actual experience taught the necessary skills. Others contended that proper training provided the foundation that allowed pilots to survive long enough to gain experience. The truth probably lay between these extremes. Training provided essential knowledge and techniques, while experience provided the judgment and confidence to apply them effectively under stress. The varying survival rates among different bomber types led to intensive investigation of which design characteristics contributed to survivability with major wing damage. While pilot skill remained the primary factor determining whether a damaged bomber could be saved, aircraft design provided the envelope within which pilot skill operated. Statistical analysis of combat loss reports from 1943 to 1945 revealed intriguing patterns. B-17 Flying Fortresses had higher survival rates with major wing damage than B-24 Liberators, despite the B-24's superior performance in undamaged condition. Lancaster bombers showed better survival rates than Halifax bombers. These differences suggested that specific design features influenced controllability with asymmetric damage. The most comprehensive study of these factors was conducted by the Royal Aircraft Establishment. At Farnborough in late 1944, engineers examined every documented case of bombers surviving major wing damage, looking for common characteristics. They also conducted wind tunnel testing and flight testing to understand the aerodynamic principles involved. The primary factor identified was dihedral angle. Dihedral refers to the upward angle of the wings from root to tip, visible when viewing an aircraft from the front. The B-17 had approximately 5 degrees of dihedral, significantly more than the B-24's 2.5 degrees. The Lancaster had 3 degrees, more than the Halifax's 2 degrees. This correlation was not coincidental. Dihedral provides lateral stability through a phenomenon called dihedral effect. When an aircraft rolls to one side, the dihedral causes the lower wing to present more area perpendicular to the airstream, generating more lift, which creates a restoring moment opposing the roll. With asymmetric wing damage that created a continuous rolling tendency, strong dihedral effect was essential for maintaining any degree of control. The B-17's high dihedral meant that even with 25% of one wing missing, the dihedral effect from the remaining wing surfaces provided significant restoring force. Pilots still had to fight the controls continuously, but the aircraft's inherent stability reduced the control forces required compared to an aircraft with less dihedral. The second critical factor was vertical tail size and effectiveness. The B-17's large vertical stabilizer and rudder provided substantial directional control authority. This allowed pilots to generate significant yawing moments that, through the coupling between yaw and roll, could partially counteract the rolling moment from asymmetric lift. The RAE engineers calculated that the B-17's vertical tail could generate approximately 25% more yawing moment than the B-24's tail at equivalent rudder deflection and airspeed. This translated directly into improved controllability with wing damage. The Lancaster's vertical tail was similarly large and effective, contributing to its survival rates. Wing structural design also mattered significantly. Both the B-17 and Lancaster used multi-spar wing designs with substantial structural redundancy. The B-17's wing incorporated 3 main spars with heavy reinforcement, while the Lancaster used a massive box spar design with exceptional strength. These strong structures meant that even severe damage often left some structural integrity, allowing the wing to remain attached even when heavily damaged. In contrast, the B-24's Davis wing, while aerodynamically efficient, was more lightly built and had less structural redundancy. Combat damage that might compromise but not destroy a B-17's wing structure could cause complete structural failure in a B-24. Several documented cases involved B-24s where initial damage was survivable until secondary structural failure caused the entire wing to separate. The fuselage design contributed in subtle but important ways. The B-17's deep, rounded fuselage provided significant side area that generated restoring forces during asymmetric flight. When the aircraft yawed, the fuselage's side area generated lift forces that partially counteracted the yaw, contributing to directional stability. The Lancaster's deep fuselage provided similar benefits. Control system characteristics varied significantly among bomber types and influenced handling with asymmetric damage. The B-17 used a relatively balanced control system where aileron, elevator, and rudder forces were proportioned to feel similar to the pilot. This harmony meant that pilots could coordinate control inputs naturally even under extreme conditions. The Lancaster's controls were less harmonized, with relatively heavy ailerons and lighter rudders, requiring pilots to consciously adjust their inputs. The B-24's control system was notably less effective than the B-17's for asymmetric flight. The ailerons were relatively small for the aircraft's wing area, providing limited roll control authority. The rudder was smaller than the B-17's and generated less yawing moment. The combination meant that B-24 pilots had less control authority to work with when attempting to counteract asymmetric damage. Engine placement also influenced survivability, though in counterintuitive ways. Engines located further from the fuselage provided more moment arm for differential thrust techniques. But engines further outboard were also more likely to be lost along with outer wing sections. The optimal placement was a compromise, and both the B-17 and Lancaster had engine positions that balanced these factors reasonably well. The location of fuel tanks within the wing structure proved critical for both immediate survivability and extended flight with damage. Fuel tanks in the outer wing sections meant that losing those sections often released fuel but didn't compromise the aircraft's center of gravity dramatically. Fuel tanks near the wing root meant that damage in this critical region often caused fuel fires or loss of most fuel capacity. The B-17's fuel tank distribution was well suited to surviving partial wing loss, while the Lancaster's concentration of fuel in the wing center section made certain types of damage more likely to be catastrophic. Control cable routing influenced whether damage affected controllability beyond the immediate aerodynamic effects. Both the B-17 and Lancaster used relatively protected routing for control cables with redundancy in critical areas. Damage that destroyed wing structure might still leave control surfaces functional if the cables survived. Aircraft with less protected or less redundant control cable routing were more likely to lose control authority completely with major damage. The research into design factors led to recommendations for future aircraft development. Post-war bomber designs incorporated larger vertical tails, increased dihedral, stronger wing structures, and better protected control systems. The B-29 Superfortress, designed during the war but incorporating some of these lessons, showed excellent damage tolerance in combat over Japan during 1945. But for the thousands of bombers already in service, design changes were impossible. Crews flew the aircraft they had been given, with whatever survivability characteristics the original designs possessed. Understanding design factors helped explain why some aircraft survived damage that others couldn't, but it didn't change the reality facing crews in combat. One surprising finding from the design analysis was that larger aircraft were not necessarily more survivable with wing damage. The B-29, substantially larger and heavier than the B-17, should theoretically have been easier to control because its larger control surfaces generated more force. But its greater weight meant that the absolute magnitude of forces was proportionally larger, and its higher performance meant it operated at higher speeds where control forces were more extreme. The optimal bomber from a damage survivability standpoint would have been a relatively slow, structurally robust aircraft with large control surfaces, high dihedral, and massive vertical tail. This description roughly matched the B-17, which partly explains its reputation for bringing crews home despite severe damage. But it also describes an aircraft with relatively poor performance in other respects: speed, range, ceiling, bomb load. The B-17 was not the highest performing bomber of World War II, but it was arguably the most survivable. The design philosophy implicit in these findings created tension between performance and survivability. Engineers designing bombers faced trade-offs at every decision point. Increasing dihedral improved lateral stability but increased drag. Enlarging the vertical tail improved directional control but added weight and drag. The design philosophy implicit in these findings created tension between performance and survivability. Engineers designing bombers faced trade-offs at every decision point. Increasing dihedral improved lateral stability but increased drag. Enlarging the vertical tail improved directional control but added weight and drag. The debate over these compromises continued throughout the war and influenced post-war bomber development. Strategic Air Command's Cold War bombers, like the B-47 and B-52, incorporated some survivability lessons from World War II experience but ultimately prioritized performance over damage tolerance. The assumption was that future bombers would operate at such high altitudes and speeds that enemy fire would rarely cause the type of catastrophic damage seen in World War II. This assumption proved only partially correct during the Vietnam War, when B-52s faced unexpectedly effective surface-to-air missiles and had to employ some of the same asymmetric flight techniques their World War II predecessors had pioneered. Beyond the aerodynamics, aircraft design, and training programs, The ultimate factor determining whether a severely damaged bomber could be brought home was the human element. The pilot's skill, strength, determination, and decision-making under extreme stress. The accounts from pilots who successfully flew damaged bombers reveal consistent psychological and physiological patterns. The immediate response to catastrophic damage was often described as a moment of suspended time where pilots felt detached from reality. Lieutenant Colonel Richard Cole, co-pilot on the famous Doolittle raid and later AB-25 pilot in the Mediterranean theater, experienced severe wing damage during a mission in 1944. His account, given during a post-war debriefing, captured this phenomenon. The explosion when the flak hit was tremendous. I felt the aircraft lurch to the left, and I saw the wing fold upward. For a moment, maybe 2 or 3 seconds, I felt completely calm, like I was watching it happen to someone else. My mind was very clear. I thought, that's going to kill us. Then the moment passed, and I was fighting the controls, and the co-pilot was fighting the controls, and we were both shouting into the intercom. This dissociation, this moment of clarity before panic could set in, appears repeatedly in pilot accounts. Psychologists studying combat stress suggested this might be an adaptive response, allowing the conscious mind to assess the situation before emotional responses overwhelmed rational thought. Pilots who successfully brought home damaged aircraft often reported experiencing this clarity and using those few seconds to form a plan before the physical struggle began. The physical demands of flying severely damaged bombers exceeded anything pilots encountered in normal flight. Captain James Stewart, the famous actor who served as a B-24 pilot, later described the mission where his aircraft sustained wing damage. Within 5 minutes of being hit, my arms felt like lead. Every muscle was burning. My hands were cramping on the control column. I couldn't have maintained those control forces for more than another 10 minutes on my own. My co-pilot and I took turns, switching every few minutes, each of us resting while the other fought the aircraft. Even so, by the time we landed, both of us were completely exhausted, barely able to climb out of the cockpit. The requirement for extreme physical exertion over extended periods favored younger pilots in peak physical condition. Statistical analysis showed that pilots under 25 years old had slightly higher success rates with severe damage compared to older pilots, likely reflecting the physical demands rather than any difference in skill or experience. Squadron commanders were typically older and more experienced, but faced challenges in asymmetric flight situations that younger pilots handled more easily, purely through superior strength and endurance. Crew coordination emerged as perhaps the most critical human factor. A pilot flying alone could not maintain control of a severely damaged bomber for more than a few minutes. But with crew coordination, control could be sustained indefinitely. The most successful recoveries typically involved explicit procedures where multiple crew members contributed to flying the aircraft. The standard technique that involved the pilot and co-pilot alternating on the controls every 5 to 10 minutes, with one always resting while the other fought the aircraft. The flight engineer would monitor the pilot on the controls, watching for signs of fatigue, and would call for switches when necessary. In extreme cases, the bombardier or navigator would come to the cockpit and physically assist by adding their weight to control inputs. Several documented cases involved as many as 4 crew members simultaneously on the controls, with one on each rudder pedal, one on the control column, and one monitoring and coordinating. This level of cooperation required excellent crew relationships and clear communication, factors that varied considerably among different crews. The psychological dimension extended beyond the immediate crisis. Pilots who succeeded in bringing back damaged aircraft often reported experiencing profound changes in their self-confidence and their relationship with their aircraft. They had proven to themselves and their crews that they could overcome seemingly impossible situations. This confidence influenced their flying on subsequent missions, sometimes positively by reducing anxiety, but occasionally negatively by encouraging excessive risk-taking. Flight surgeon Major Donald Flickinger studied combat stress among bomber crews and documented what he called post-damage resilience syndrome. That had survived major damage and successfully returned home showed different stress patterns than crews that had not faced such challenges. They had greater confidence in their survivability but also showed symptoms of hypervigilance, constantly monitoring for signs of damage that might require similar heroic efforts. The relationship between pilots and their aircraft took on almost mystical qualities in some accounts. Pilots spoke of feeling their aircraft, of knowing through the controls what the aircraft could and couldn't do, of having intuitive understanding that transcended technical knowledge. This anthropomorphizing of machines might seem irrational, but it reflected genuine skill development where pattern recognition and muscle memory enabled responses faster than conscious thought. Lieutenant William Wheeler, a B-17 pilot with 35 missions, described this relationship in his memoir. After the first 10 missions or so, flying the aircraft became automatic. I didn't think about what the controls did, I thought about where I wanted to go, and my hands and feet made it happen. When we got hit and lost part of the wing, that automatic response was actually a problem at first. The aircraft didn't respond the way it should, and I had to consciously override my instincts and learn a new way of flying, right there in the moment with German fighters shooting at us. This need to override learned responses and develop new control techniques in real time represented a cognitive challenge as demanding as the physical challenge of maintaining control inputs. Pilots had to simultaneously manage multiple tasks, maintaining control, navigating, communicating with crew, monitoring engines and systems, watching for fighters, and making strategic decisions about whether to continue toward the target, jettison bombs, head for neutral territory, or attempt to reach home base. The decision-making under uncertainty was perhaps the most cognitively demanding aspect. Pilots faced choices with incomplete information and potentially fatal consequences. Should they gain altitude, which provided more options if engines failed but exposed them to fighters for longer? Should they maintain speed, which improved controllability but stressed the damaged structure? Should they jettison the bomb load, which reduced weight and improved performance but meant the mission was a failure? There were no objectively correct answers, only judgment calls based on incomplete data and uncertain outcomes. The emotional toll of these experiences affected pilots long after the missions ended. Post-traumatic stress disorder was not recognized as a formal diagnosis during World War II, but the symptoms were certainly present. Pilots who had fought damaged aircraft for hours reported nightmares, hyperstartle responses, and persistent anxiety about flying. Some requested transfer to non-flying duties. Others coped by flying more missions, perhaps seeking to prove that the traumatic experience hadn't diminished their abilities. The social dynamics within squadrons created informal support systems. Pilots who had survived major damage became resources for others, sharing their experiences and techniques. Ready rooms featured discussions where techniques were debated and refined. This peer-to-peer knowledge transfer was probably more influential than formal training for many pilots, providing practical wisdom that official documents couldn't capture. The cultural context also mattered. In American units, there was often an emphasis on individual achievement and heroic narratives. Pilots who brought back damaged aircraft received recognition, medals, and publicity. This created motivation to attempt recoveries rather than bailing out, but also created pressure to succeed that added to the stress. In British units, the cultural emphasis on stoicism and understatement meant that extraordinary achievements were often described matter-of-factly, with less individual recognition, but perhaps less pressure as well. The lessons learned from bomber crews flying with major wing damage influenced aviation development and safety practices long after World War II ended. The experiences, techniques, and insights gained under combat conditions provided foundations for improved aircraft design, pilot training, and emergency procedures that continue to shape aviation today. The most immediate post-war application came in the design of heavy bombers for the emerging Cold War. The B-36, B-47, and eventually the B-52 incorporated structural redundancy, control system protection, and flight characteristics informed by World War II damage experience. While these aircraft were designed primarily for nuclear strike missions at high altitude, where conventional damage seemed unlikely, the design philosophy emphasized survivability principles learned from combat. The B-52 Stratofortress, which entered service in 1955 and remains operational today, exemplifies this legacy. Its large vertical stabilizer, significant dihedral, multi-spar wing design, and protected control systems all reflect lessons from World War II. While B-52s rarely faced the type of conventional damage that was common in World War II, instances during the Vietnam War where B-52s survived severe battle damage validated the design approach. One notable incident occurred in December 1972 during Linebacker II operations over North Vietnam. A B-52D suffered catastrophic damage to its vertical stabilizer from a surface-to-air missile. The pilot, Captain John Mize, maintained control using aileron and differential thrust alone, flying for over an hour before successfully landing at Utapao Air Base in Thailand. Mize's techniques directly paralleled those developed by World War II bomber pilots 30 years earlier. The techniques developed for asymmetric flight influenced commercial aviation as well. Modern airline pilots receive training in handling asymmetric thrust conditions following engine failures, and these procedures incorporate principles learned from wartime experience. The emphasis on crew coordination, workload management, and physical relief for pilots during emergencies all trace back to lessons learned in combat. Flight simulator technology evolved partly in response to the recognition that certain emergency procedures were too dangerous to practice in actual aircraft. The military's investment in simulator development during the 1950s and 1960s enabled pilots to experience and practice responses to severe damage in safe environments. Modern full-motion simulators can replicate the control forces, aircraft responses, and decision-making challenges that World War II pilots faced, allowing contemporary pilots to develop skills without risking their lives. The physiological research into pilot fatigue and control force limits, stimulated by World War II experience, contributed to the development of powered flight controls in post-war aircraft. Hydraulic and later fly-by-wire systems eliminated the need for pilots to physically overcome aerodynamic forces on control surfaces. While these systems introduced new failure modes, they dramatically reduced pilot workload and fatigue, making long-duration flights feasible with smaller crews. The psychological research into combat stress and decision-making under pressure influenced military training broadly. The military's understanding that stress affects cognitive performance, that training must include realistic stress exposure, and that crew coordination requires specific skills beyond individual competence, all developed partly from studying bomber crew performance in extreme conditions. Several of the pilots who successfully brought home severely damaged aircraft became influential in post-war aviation. James Stewart, the actor who flew B-24s, remained in the Air Force Reserve after the war, eventually reaching the rank of brigadier general. His advocacy for improved pilot training and aircraft safety influenced Air Force policy. Richard Cole, Doolittle's co-pilot, had a distinguished post-war career in the Air Force, contributing to transport aircraft development and training programs. The aircraft themselves largely disappeared after the war. Of the approximately 12,700 B-17s built, only about 40 survive today as museum pieces or restored warbirds. The Lancaster, with 7,377 built, has fewer than 20 survivors. These survivors serve as physical connections to the wartime experiences, allowing modern observers to appreciate the size, complexity, and capabilities of these aircraft. Several museums have preserved aircraft with visible battle damage, providing tangible evidence of the punishment these bombers could sustain. The National Museum of the United States Air Force displays a B-17G with extensive flak damage to its wings and fuselage. The Imperial War Museum Duxford has a Lancaster that sustained battle damage. These exhibits help visitors understand the conditions crews faced and the challenges they overcame. The historical documentation of asymmetric flight incidents has improved significantly as archives have been opened and veterans have shared their experiences. The detailed incident reports, pilot debriefings, and engineering analyses that were classified during and immediately after the war have gradually become available to researchers. This documentation allows systematic study of what worked, what didn't, and why. Scholarly analysis has revealed some uncomfortable truths about the incidents. While the successful survivals were remarkable, they represented a small fraction of aircraft that sustained major wing damage. Most crews facing such damage did not survive, either because the damage exceeded controllability limits, because they were unable to escape enemy territory, or because secondary failures made survival impossible. The survivors, while extraordinary, were outliers rather than typical cases. The question of whether the survival techniques developed during the war would be applicable to modern aircraft receives occasional attention from aviation safety researchers. Modern airliners are fundamentally different from World War II bombers. They're faster, fly higher, have different structures and control systems. But the basic principles of asymmetric flight remain unchanged. If a modern aircraft lost a significant portion of one wing, the pilots would face similar challenges to those faced by bomber crews in 1944. Fortunately, such damage is extraordinarily rare in modern aviation. Structural failures are prevented by rigorous maintenance and inspection programs. Mid-air collisions are prevented by sophisticated air traffic control. The scenarios that routinely caused major wing damage in combat simply don't occur in civil aviation. The last commercial airliner to sustain major wing damage and successfully land was probably an incident in the 1970s, and even that involved relatively minor damage compared to what bomber crews faced.